All right, it's 4:10 p.m., so if you all would take your seats. Are we ready, Ben? Let's do it. Welcome to the Quantum Internet Research Group meeting here in Prague, and today we have 2 hours, as you know. This session is a tutorial session. I'm Rod Van Meter. I am one of the working group co-chairs. My co-chair, Stephanie Vayner, is not here today, but we have with us Tracy Northup from Innsbruck, who's going to help me with the tutorial. So we'll do that for a couple of hours today. We're going to try to take about a 5-minute break just to give everybody time to stretch their legs about halfway through. And also, this session is the tutorial. Tomorrow will be the working group meeting where we're going through the existing set of drafts and whatnot. Next page. So yes, as you know, we are in the Grand Ballroom. For those of you who are online, or if you need the URLs, there's the connection. Next page. And tomorrow will be 11:20. We'll be downstairs in Congress Hall for the working group meeting there, and we'll cover the active set of internet drafts, of which there are about 3, although they're not all correctly tracked in the system yet. There are at least 3 that are relevant to what we're doing, and a couple of other things. And let's see, next page. So the history and status of this group, just very, very quickly, for those of you who are in the room for the first time or hearing about this for the first time. Stephanie originated the idea of having this working group, this research group, in January of 2018. I gave a presentation remotely at the IRTF Open in March of 2018. We opened the mailing list after that, and we were approved tentatively as a proposed research group in November and met in Bangkok, where we had an overflow room, 120 or so people I think were on the blue sheets. And our proposed plan, which we may or may not stick to in its entirety, is to meet once a year here at IETF, and once a year at a quantum conference, and once a year virtually or online, just sort of roughly. Okay, next slide. So today, let's see, we have the blue sheets going out around. We have a note taker and a Jabber scribe already taken care of, so we're in good shape there. And tutorial-wise, although the agenda says first half me and architectural concepts, and second half Tracy and implementations, we're actually going to sort of switch back and forth a little bit as we go. Instead, it's going to be a little bit more mixed. And we would like to make this as interactive as possible. So if there's anything along the way that you have a question about, feel free to step to the mic and ask. We'll recognize you at sort of a reasonable stopping point, and consistent with forward progress, we'll take as many questions as we can during the course of this. Let's go ahead and switch to the other laptop. Yeah. Any comments or questions on what we're doing before we get started? We have presentation. Good. All right. So rough outline of what we're going to talk about. I'm going to give you a few minutes on the TLDR version of what a quantum network is. Spend some time talking about what applications we might run on it, which should be kind of why you care. Some basic concepts and terminology, and some math and whatnot, and then somewhere down and through here we'll switch over and have Tracy do some of these parts as we go. So roughly the vision has been around for a while, but was articulated particularly well in a way that kind of set off a bunch of work by Jeff Kimball from Caltech in an article in Nature in 2008. And the basic idea is that you have quantum nodes where information is stored and processed. They're like quantum computers, perhaps using atoms, perhaps not. And you use some sort of quantum channels for connecting them for information transport and creation of distributed quantum states as we go. And roughly this will give you the general idea of a quantum internet. And you can see it's really sort of highly realistic network topology, the kind we all see out in the real world every day. Roughly, there are two kinds of quantum networks. There are unentangled networks, which are good primarily for quantum key distribution, which is essentially making shared secret bits across a network where the secrecy of those bits is guaranteed via the underlying physics rather than some sort of mathematical function. And these networks exist. They are limited in distance, and they're single purpose, and they have other constraints which some of you all are aware of, but they do exist. At the other end of the spectrum lie entangled networks, good for many different purposes, cryptographic functions, high precision networks, connecting quantum computers into a real quantum internet, and covering long distances and whatnot. And these things are particularly difficult to build, but Tracy and other people are working on that. And in between these two major categories of networks, there's a series of steps defined by Stephanie and her collaborators, and we'll show you just a little bit more about that as we go. Axel Dahlberg from Stephanie's group presented some of this in Bangkok with a really good overview of that. All right, so in order to understand quantum networks, the single most important concept you have to understand, and one that's among the most misunderstood concepts anywhere in the world, is entanglement. So if we have two quantum systems, one on the left and one on the right, and they are in some sort of entangled state, what that means is that their behavior is shared in some fashion and they are not completely independent. If you measure the one on the left to figure out what it looks like, what it's actually doing, you will find that it's either pointed up or pointed down, and in this case it was pointed down. At the same time, you will learn what the one at the far end is, even if these two systems were far apart. This is sort of the basic idea of entanglement. I can't see a clock. How are we doing? We don't have a clock, do we?
We don't.
That I can see. My life would be better if I could see one. Anyway, so quantum entanglement showed up in the New York Times, well, about 5 years ago now, with an article, "Is Quantum Entanglement Real?" And the particular reason the New York Times was talking about that in 2014 was because it was the 50th anniversary of a particularly famous paper in the physics community by a guy named John Bell, and that was on the Einstein-Podolsky-Rosen paradox. Prior to this point, as you'll learn, as Tracy will explain later, Einstein and others had some serious concerns about the behavior of quantum mechanics, and Bell said there's a way we can test this statistically. So, the job of a quantum repeater network is to make this entanglement end-to-end between a pair of nodes, modulo some arguments we're not going to get into about the ordering of events and whatnot. And importantly, entanglement is a consumable resource. And so we have to make lots and lots of it as we go. That's the job of the quantum network, is to regenerate this entanglement sort of continuously. So if that's the job of the network, then the job of a repeater in the network, a single individual node, is first to make entanglement over a physical link with some sort of neighbor. Second, to be able to take that entanglement that it has with individual neighbors along a path and use that to create entanglement between two endpoints, so spanning multiple hops. Third, to monitor and manage errors as it goes. We'll look at a couple of techniques. One of the ones we'll talk about the most is what's called purification. There's also quantum error correction. And fourth is to participate in the management of the network itself. So routing protocols and security and path setup and teardown and multiplexing and all those other sorts of things that people in this room know better than anybody. So if that's the job of a quantum repeater, then, and an individual network, then the job of a quantum internet, as opposed to a quantum network, is to do all of this across heterogeneous networks, both physically and logically, in an environment with minimal trust between those networks, and that includes having no knowledge of the internals of the autonomous networks, the equivalent of the internet's autonomous systems, and possibly in the presence of malicious nodes. So all of this is the kind of area where the people who are designing and building quantum hardware need the help of the people in this room. Okay? These are the kinds of areas where the quantum physicists not only, I'm going to say this even though, in front of a physicist, even though Tracy's here, the physicists not only don't know a lot of these things, in a lot of cases they don't know what they don't know. Right? There's an awful lot of problems that have to be solved from having a physical layer in a network up through layers 2 through 9 or however many layers you want to have. Right? So that's the, all right, go on. So how many protocol layers you happen to care to have. So the job of the people in this room is to help guide those experimentalists who are building those networks and help us to build complete systems. The same as was done with radio and fiber and everything else as we went over the course of the last 50 years. Several years ago, let's see, how long ago was this now? Do you remember when this paper was?
That was 2014, I think.
2014, I think. The group of Liang Zhang from Yale University defined a set of generations of networks. They defined what they called 1G, 2G, 3G networks, and we're going to talk a little bit more about what those different kinds of networks actually are and represent. You'll notice that on the left, they describe 2 classes of errors. There's loss error, meaning the loss of your individual photons as they're going down a fiber, and then there's operational error, noise in the system, decay of your memory, and whatnot. So the loss error obviously operates at the link layer, and the operational layer you have, or the operations errors we have to deal with at the end-to-end layer. There's a whole bunch of stuff that has to be done. You can't deal with this simply hop by hop, and we'll explain how that is as we go. So what are these networks good for and not good for? Very briefly, quantum networks are about new capabilities. Some people sort of naively, when they first come in, they hear quantum, they think something fast is going on. They think maybe we'll either be able to violate the speed of light and transmit information faster than the speed of light. I'm here to disappoint you and tell you that's not the case. And it's also not the case that quantum networks are going to be some pathway to terabit, exabit, yotta-bit per second kinds of networks. That's not what we're trying to do here. We're going to bring in new kinds of capabilities into the networks, improvements in the number of communication rounds for certain distributed protocols, higher precision, scalability of distributed systems, and whatnot. All right, so going a little bit more into the applications themselves, I divide the set of applications that we can do with a quantum internet into 3 large areas. There's distributed cryptographic functions, sensor networks, and distributed computation. And these are just a few of the algorithms or proposed uses for these that have been proposed by theorists over the course of the last couple of decades. And part of our job as engineers is to try to figure out which ones of these are practical, in a sense, could be actually implemented on hardware that can be built sometime in the relatively near future, and would actually be applicable to systems out in the real world. Notice that everything in the distributed crypto bubble is intended to reduce our dependency on public key cryptography, one-way functions, computational complexity, those sorts of topics. As it happens, one of the things we've realized in the work that we've been doing, the crypto functions are relatively low bandwidth in terms of their demands on the network. The sensor networks are high to very high bandwidth, and the distributed computation is also high to very high bandwidth. So certainly in the short run, the crypto functions are going to be the thing that's going to be driving adoption. The others are going to take a little bit more time to get there. But let me go through an example with each one of these categories and show you the kinds of things we want to do. This particular one goes back to an internet draft that Shota Nagayama sitting over there and I wrote back in 2014. We never finished getting this to RFC status, and since then it's been superseded by some other work that's happened in IPsec-ME. But the idea is to augment IPsec with keys that were generated using a quantum network, using quantum key devices. And this would take probably a separate dark fiber that runs through some particular infrastructure, and of course the ultimate data communication actually happens over the internet itself. And if we divide this out a little more abstractly, you're going to have two networks. You're going to have the quantum network and the IP network. And over the quantum network, between two QKD devices, you're making keys. You're making distributed, shared, secret bits whose secrecy is guaranteed by the certain aspects of the devices. We can have all sorts of discussions about that, but that's the idea, right? And those keys are exchanged with the IPsec gateways in some particular, in some secure fashion, and then they're actually used to encrypt data that's transmitted across the IP network. So that's the basic structure. This could also be applied to TLS. Sheila Frankel, I think, was the one who proposed this. We actually did a little bit of analysis on it. Obviously, at the client end, you're going to need a single connection, and at the server end, you're going to need many connections. And for the client's connection, you need to be able to generate maybe 100 bits per second or something. And at the server end, you're going to need megabits on up in performance of this. So the IPsec use case is pretty symmetric, whereas the TLS case is concentrated, same as standard network architectures, right? So, is this useful? How long is it useful for? Let's look at some use cases with a couple of different possibilities for the key exchange mechanism and a couple of different possibilities for the bulk data encryption. Diffie-Hellman plus AES, QKD plus AES, QKD plus something I'll call super AES, and QKD plus a one-time pad. And let's look at data that we're encrypting today. At some point, so you're encrypting data today and you're sending it across the network. At some point in the future, it may become possible to factor large numbers or otherwise do some particular mathematical operations. Farther on down the line, someone may find some vulnerability in AES, something we don't suspect that actually exists today. And then maybe in some sort of hypothetical straw man, maybe it's possible to test all of the keys, all of the possible key combinations. So if you encrypt data today, the data is secure from now until someone factors a number. If they have recorded your encrypted conversation today that's being sent across the network, and then in 10 years this factoring becomes possible, then they can decrypt the conversation you're having today 10 years from now. With QKD plus AES, instead it stays secure until AES is actually broken. And if you use some sort of super AES, maybe it stays that way until some hypothetical such as testing all possible keys becomes possible. And ultimately, of course, we want to get to using this as a one-time pad, and theoretically it'll stay secure forever. Right? This is possible today. It's possible to go out and buy boxes that do quantum key distribution and work with AES and do your encryption this way today with a lot of caveats and a lot of limitations. Excuse me. So the question is the gap between these two states of future history actually interesting? The gap between when factoring becomes possible and when AES gets broken. If so, you should be looking at deploying QKD today. By the way, if you haven't seen the website weakdh.org, if you are a particular cryptographer, I would love to have the opinion of people on that particular approach. Today, if you want to do this QKD plus AES, you're going to need data rates on the order of bits per second in order to roll your keys over in sort of reasonable time. With super AES, it's going to be the same. Whereas with one-time pad, obviously you're going to need to be able to reach up toward billions of bits per second in order to do this sort of reasonably. So as you can see, we've got sort of 9 orders of magnitude of performance range there. As performance improves, new capabilities will come online. It'll become possible to do new things. All right, so that's the crypto use case, the crypto scenario from the big bubble that I had in the 3 bubbles. Let's talk about distributed computing. There's a concept known as blind computation, which is secure quantum time sharing, give or take. I'm sure many of you recognize that DEC System 10 up there. Some of you may have actually programmed it. The original ARPANET vision was taking a system like that and a network that looked like this. This map or a copy thereof still hung on the wall at ISI when I arrived at ISI in 1986, although this is the 1973 version of it. So this is your ARPANET, and then you have some small system in front that behaves as a front end, and we're going to connect our small quantum computer at our house or laboratory and connect it to a mainframe across the quantum internet, and everything's going to be hunky-dory, right? All this is going to be cool. Well, that's not bad, right? It's not bad. But why is that different from what we can do today, where literally my group in Japan right now is literally connecting via the existing internet to IBM's research center in Yorktown Heights and using their quantum computers that are in a laboratory in New York remotely from Japan. So, right, we can already do that, right? So what do we need a quantum internet for? We can already build distributed systems like that. Well, what you get by being able to do this in a distributed fashion and doing this using a quantum internet and this blind computation is it allows us to execute a computation on the server in which the server learns nothing about the client's data, either the input or the output, nor even the computation, except some sort of upper bound on the size of the computation itself. So in that sense, it's actually even stronger than the classical version of, or the classical homomorphic encryption, if you're familiar with that. So I really love this. This is, I think, ultimately one of the driving reasons to build a quantum internet, and it's also going to open up a whole lot of interesting applications across a variety of things. And this has actually even been demonstrated in the laboratory at sort of the 1 qubit level. We're not talking about some giant computation. But doing it via some analysis, we've actually found that it's going to take very high data rates in order to execute this for large computations, maybe 10 to the 10, somewhere around there. So this is a long-term goal for getting to the point where we actually have a system for connecting complete quantum computers via the internet and building complete distributed systems as we go. The third scenario that I mentioned was sensor networks. So I sort of define sensor networks sort of broadly. There are algorithms that have defined for doing high precision clock synchronization. There are algorithms for doing high precision position finding. And in this particular case, there are also algorithms for taking distributed quantum states and using them as essentially a phase reference in astronomical interferometry, which allows you to get higher resolution images than can be done using the existing interferometry that's done between antennas, like the couple of antennas in this picture. So this looks really great too, right? In theory, we can use this for sorts of cyber-physical uses and improving different kinds of sensor networks as we go. Sadly, this one's also an even higher bandwidth. This is probably going to take something like 10 to the 11 operations per second or bits per second, entanglements per second in order to do this sort of usefully. And finally, this is an area I actually haven't spent much time looking at because I'm not certain it's actually practical, but there are a number of research papers out there that are showing that given the existence of entanglement, we can actually get exponential reduction in the number of rounds you need to solve particular problems, exponential as the size of your network grows. So there's a set of things that are out there, potentially worth taking a look at some point. Technical demands. Some of these require only the ability to actually measure photons that come at you. So you're sitting at home, you don't necessarily have to have a complete quantum computer at home, but you've got a pipe coming in, you've got a fiber or something coming in, and individual photons are coming out of that fiber. You need the ability to measure those. That's at one end of the technical spectrum. The other end of the technical spectrum runs all the way from all the way up to having really high precision quantum memories and a large scale quantum computer at your node in order to actually execute interesting algorithms over that. And that's sort of a relatively long way away. This is, on the lower left there, is a series of stages that the evolution of these networks will go through. Again, that's from the roadmap that was actually developed by Stephanie Vayner and her team. Any questions on applications? Now might be a reasonable time to ask for the first round of questions. I've been talking for about 20 minutes now. 20 minutes, yes. Questions? I can't possibly have convinced everyone that all of this is entirely practical. Which means that if there are no questions, that none of you have understood any of it, right? I don't believe either of those things to be true, so I'm sure someone here has a question. Excellent. Questioner number one, please remember to state your name for the record.
Kent Watson. My question is, why would you need repeaters in a quantum network? I thought quantum was independent of distance.
So an important thing to note, which I should have said and emphasized repeatedly way up here at the front, so to speak, is that quantum repeaters are not the same thing as classical repeaters. Don't blame me, don't blame Tracy, blame whoever it was that wrote the first paper on these things about 20 years ago and called them repeaters. They are not like classical repeaters. They are not amplifiers. They are nodes that are actually active devices doing a particular set of operations that are used to help us extend entanglement across multiple hops. And we're going to get into the architecture of that stuff for the next hour. So, good question, though. Thank you for bringing that up, since that was a good technical point. Yes?
So maybe quickly to address his comment that quantum is independent of distance. I mean, I think that might be, maybe he's referring to the sense of if you can create a quantum state as a resource to use for your computation, then yeah, at that point it doesn't matter to us how far apart it is, but it's in order to create those quantum states over long distances that we then need repeaters. So the repeaters are kind of for the creation of quantum states as resources, and I think we'll get more to the details of that coming up.
Does that help? Good. Yes?
Hi, Giovanni, SIDN. So when you say when your team in Japan connects over the internet to the quantum computers in the US, what exactly can they do with that, and how does it actually work? So like more practical.
That's a long discussion.
Right?
At the moment, so my team in Japan is using a 20-qubit superconducting computer that's in a laboratory in Yorktown. I was chatting with my team via Slack just right before we started this, and they're actually doing some stuff right now. But those existing machines, the 20-qubit systems, are good enough to start testing stuff and start running very, very tiny algorithms on top of them, but not like anything that you would really recognize as sort of a reasonable computation. It's still pretty much at the test stage. My group is working on compiler technology, so we're trying to figure out how to optimize programs that are written by a programmer in a Python-based toolkit called Qiskit. This is the Qiskit T-shirt. If you use Qiskit, Qiskit has functions built in for logging into the remote system. Excuse me, and sending your program from your laptop to their controllers over there, and then they execute it 10,000 times over there, and then they give you back statistical data. There's no real interactive control. It's very much batch stuff that you can do, and the sets of things that you can do with it, there are a handful of very small algorithms that you can run on that and then sort of squint and say, yeah, the data kind of looks like what it was supposed to. But they're getting better rapidly. IBM is releasing new machines a couple of times a year. A couple times a year might be a little bit of an exaggeration. But there are a bunch of people out there who have machines that are actually available now on the network. Some of them are available for free. IBM has one 5-qubit computer and one 14-qubit computer that anybody can go log in on and create an account and run things remotely from here. So do Rigetti and Google and other people. Well, some of those aren't, I don't think, actually public yet. And Tracy's group in Innsbruck is actually building computers on a different technology known as ion traps. So there's a bunch of stuff that's out there. It's still early, but there's a lot of progress being made. Any comments?
No, or I think he has another question.
No, just thanks. Now it feels more concrete. Thanks a lot.
Yeah. I mean, maybe I mean, in a nutshell, they can't yet do anything that classical computers can't do, but the progress is really impressive.
Hujun, so you mentioned that there's already today have a quantum key distribution device available today. So I saw if we argument that with IPsec, for example, would that mean that you can get rid of like Diffie-Hellman?
That you can carry what?
Get rid of Diffie-Hellman.
Yeah, so that's replaced Diffie-Hellman with the quantum key distribution. Some of the products, I'm not familiar with the details of all of them, but I know in at least one case what they're actually doing is they're actually running 2 layers of encryption. They're running one bulk encryption using keys generated via standard Diffie-Hellman and another layer using keys generated by QKD. And you can either view that as a way to mollify people who don't believe in QKD or view it as they don't have faith in their own device. Sort of take your pick. But
So with those QKD devices, would that the QKD key is generated on those devices, or just a transport mechanism?
The keys are generated at the QKD gateways, at the opposite ends of the fiber.
Okay, thanks.
Sue, I saw you moving that way. Does that mean there was a question via Jabber or something?
I think we should probably move on, though.
Okay. Time-wise, we should move on. So some basic terminology and questions or concepts. 1, 2, 3, 4, 5, 6, 7 concepts. I'm not going to go through all of these in detail. These are sort of vocabulary for you to vocabulary homework for you to take home and look at. You'll get a few of these as we go. A few terms we will actually use in the course of this. Quantum amplitude means the amount of your total quantum probability wave function thingamabob that is in a particular state, and it's represented by a complex number. A pure state means a quantum state where your hardware actually worked the way it was supposed to. Okay? It actually did what it was supposed to do. And we describe that as having a fidelity of 1.0. A mixed state is one that has noise and errors in it and has fidelity less than 1.0. So mixed state, some people talk about, and we'll get into superposition and entanglement and things like that. People from sort of outside the field occasionally use the term mixed state when they're talking about those things. Don't get confused. Mixed state means your hardware sucks, right? So an entangled state, we've already talked about a little bit. One that has sort of these shared properties means it can't be separated. And a Bell pair is a particular type of entangled state. It's the canonical form of 2-qubit state, which we're going to get to. So superposition, right? So we've all seen waves. You've seen another wave like this, 2 with slightly different frequencies. You add them up, and you get something that looks like that, right? This is normal waves. At the moment, we're not doing anything at all quantum. But this gets you what you call interference. So over here at the left, where your 2 waves are in phase, they add up, and you get what's called constructive interference. And there in the middle, where the waves are out of phase, they cancel out, and you get what's called destructive interference. This happens at the quantum level with individual photons and individual electrons and whatnot. That's one of the key concepts that's actually required to understand quantum computing. All right, so couple of things about the basic mathematical notation. Dude named Dirac, who was one of the people who helped create quantum mechanics, defined what's called the Braket notation. You'll see there a couple of examples or 3 examples of 2-dimensional vectors. And what we do is we write this like this, using this funny vertical pipe and an angle bracket. That's what we call our 0 state. So that vector is defined to be the 0 state. This vector is defined to be the 1 state. And if you put them together, whoops, let's see, you get something that looks like that, a state that's partly 0 and partly 1. This is how we write down a quantum state. This is Dirac's Ket notation. You might have guessed from the title of the slide already. There is also a thing called the bra notation. The bra points one way, the ket the other, and you put them together and you get a braquette. Right? How nice. When you have 2 qubits, when you have 1 qubit, you have 2 amplitudes because you have 2 states, 0 and 1. When you have 2 qubits, you have 4 states. You have 4 amplitudes, 0, 0, 0, 1, 1, 0, 1, 1. When you have 3, you have 8 amplitudes. And you can go on from there, exponentially large number of possible amplitudes in this. There are 2 to the n elements in what we call your state vector, which describes the system. And each one of those amplitudes is a complex number when you have n qubits in your system. Okay? The probability of measuring, so when you go and you look at this system, you collapse the state so that you find it in exactly one of those states, not the superposition of all of them at the same time. And the probability of finding each of them is the absolute value of that amplitude squared. And each one of those, like I said, is a complex number. They can even be negative. And normalization requires that all of the probabilities add up to 1. There's a thing called the no cloning theorem. I'm not going to go through this, but basically it means you can't make unentangled copies of things, which limits our ability to do error correction and store and retransmit on failure and things like that. And with that, let's see, you want to take this part?
Sure, yeah. Should we maybe quickly ask if there are questions at this point about the last section? Questions at this point about the previous section? Yep. Any questions for either of us about the previous section before I move on? Okay. So we're going to try to kind of
stand really close to the mic.
Really close to the mic. Okay, here we go. So this is kind of a little snapshot from a historical perspective about entanglement. And to give a little bit more insight into this concept that Rod has already mentioned, which are Bell pairs, and also the concept of non-locality. And so this is the kind of Cliff Notes version here for you, with kind of the 3 main actors, historically speaking. There's a key paper by 3 authors, one of whom was Einstein in the 1930s, with the very famous claim that either quantum mechanics is non-local or else it is incomplete. And somehow, you could imagine that maybe Einstein was hoping that then he, in the future, would go on and be able to fill in this hole here. Later on, in the 1960s, John Bell, Scottish physicist, comes along and points out, looking back at Einstein's paper, even if it is incomplete, that does not get you around this non-locality. These are both theoretical perspectives, and then a series of beautiful experiments. One of the earliest experimenters was Alain Aspect in Paris, really pointing out that this non-locality is not, what's known as a local hidden variable theory cannot explain experiments, and that therefore we have to sort of live with this idea of non-locality. So I'll go into a little bit more detail now about these kind of 3 different comments. So Einstein, Podolsky, and Rosen, this is this 1930s paper. The title of the paper is Quantum Mechanics Complete. And so we can understand that as saying, before we measure a system, does it have a definite state? And this is what you heard Rod referring to when he's saying that we are going to do a measurement and we're going to understand that measurement as a collapse into a particular state. And so should we think of that system as having had that particular state before we measured it? And so what do we mean by this kind of reality? What we would describe, so here's a quote from this paper. If without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So as physicists, we talk about local realism, and this is what we mean by the realism part, that there is once we measure something, we're going to get this particular answer. So what's the argument behind this Einstein-Podolsky-Rosen paper? That we're going to assume that there's a locality, that is, we can't signal faster than the speed of light between distant locations. So no immediate signaling. And also we're going to assume that a single measurement generates a single result. And the result of what they come out of after some arguments is to say that quantum mechanics is either non-local, it either violates the first statement, or it's incomplete, there's something missing. Okay, so that's disturbing, and that paper led to what were essentially a lot of philosophical arguments for 30 years, and the beauty of John Bell's contribution in the 1960s was to take this beyond a philosophical perspective and really formalize the mathematics of it, and say, can we add some kind of add something to quantum mechanics, and in particular, can we add some kind of hidden variables that are sort of lying beneath the surface that parameterize our system and actually tell us what the measurement will be? And does that save quantum mechanics from this non-locality, from this fact that maybe the, and so what does Bell do? He derives a very specific inequality, and he shows that if you have a local hidden variable theory, it has to satisfy that inequality. And then you can take quantum mechanics as we know it, plug it in, and show that quantum mechanical states violate this inequality. So if quantum mechanics is true, we have to accept that then this non-locality. Again, that was this theoretical perspective, and then quite soon afterwards, the message is quantum mechanics cannot be described with a local hidden variable theory. And so what do you do experimentally with that? You take the inequality and you find ways to test it in the laboratory. And those experiments have now been going on really for, this is kind of the 5th decade of experiments. And the first experiments were very beautiful, but one could also point out ways in, so-called loopholes, ways in which you could still find ways for maybe hidden variables to sneak in. And the most kind of recent and exciting progress here was 3 parallel experiments in 2015, which, close the major loopholes. People can always kind of think of interesting loopholes, and will continue to do so, and that's very nice. But I think that the ones that people have been most concerned about for these Bell inequalities have been closed experimentally. And so it's really a beautiful experimental demonstration that that quantum mechanics is very weird. There's also, I'm talking about a Bell inequality. There are many different kinds. The most famous is what's known as the CH-SH Bell inequality for Clauser, Horn, Shimoni, and Holt, who wrote a paper on this in the 1970s. So this brings us to these Bell states. And so in the process of deriving this inequality, you can kind of establish that there are some maximally entangled states. There are some states essentially that maximally violate these inequalities. And so they're sort of the weirdest states, the most quantum states. And we give them these names that we always use for them, this psi plus and minus and phi plus and minus. And it's states of 2 quantum bits. So with this notation that Rod has already introduced, the first 0 or 1 is labeling the first quantum bit, the second one is labeling the second quantum bit. And so, for example, if we look at the first one, the first state in the upper left-hand corner here, this phi plus state, we're saying that either both of your quantum bits are in the state 0 or they're in the state 1. We normalize it with the square root of 2. But the point is that if person A is in possession of one quantum bit, B in possession of the other, wherever they are, the minute that, or instantaneously, we believe when A measures her quantum bit, that we can immediately predict what the outcome of B's measurement will be. And in this case, if it's 0, it will be 0. And for psi plus and minus, if it's 0, it will be 1. So these are these canonical Bell states. Entangled states, we say that they can't mathematically be written as separable states. And they can also be used as a basis set to rewrite any state of 2 quantum bits. We like to describe these states as a resource, both for quantum communication and for quantum computation. So we talk, as I suggested before, about 2 people sharing a Bell pair, and when we mean that of these two qubits, one person is in possession of one, the other is in possession of the other. And that bell pair is exactly what can be used to generate secret keys. And that's kind of back to what Rod pointed out in his earlier slides. You can imagine kind of sharing a bell pair and then either adding on top of it something like AES, which would kind of, or sharing many bell pairs, either adding on top of it AES, or the best thing would be to be able to use those bell pairs in order to generate a one-time pad. But of course, you would need a very high rate of bell pairs that you're sharing between each other. If you have just one bell pair, ideally then that lets you send one quantum state from one person to the other in what's known, for better or worse, as quantum teleportation. And yes, so we want to, I've suggested, or I've explained that once one person performs a measurement on her half of this bell pair, then that person can predict immediately what the result of the second person's measurement will be. Does that mean we can send signals faster than light? No. And one can prove this formally. And for quantum computing, right, we're just going to keep saying this because we know how often people come up and would like to talk to us about information traveling faster than the speed of light, so we're trying to tamp that down early on. Right, maybe there's some physics that we don't know about, but in the physics that we're working with now and the physics that we understand to describe the world that we live in, it might look like they're signaling each other, but they're not. And the important thing is that even though person A knows she can predict what her partner's measurement will be, that's not yet the same as signaling. And they will also need to exchange information over a classical channel, and that's going to be the bottleneck in terms of actual communication between the two of them. So they're not going to be able to use their quantum states in some special way that violates that happens faster than the speed of light. Right, so now with that kind of idea about bell pairs as a resource that two parties can share over some longer and longer distance, we can move to one application, which is teleportation. Maybe I'll hand it back to Rod here, but first ask if people have questions about entanglement.
Hi, this is Dino. Regarding entanglement, could you get a head start on the computation with a good probability that it might be right and classical later verifies that the prediction was correct? And if not, you just discard your computation in the middle of the process?
So kind of a hybrid computation
Say we'll take the benefit of the doubt that it does go faster than speed of light by trying the quantum state, and then we get a verification later from the classical channel that it was wrong, and then we give up. But if it was right, we got a head start.
Yeah, so I think there's maybe, maybe you have something to add, but I guess I would say that we can't sort of take shortcuts with this speed of light story. So there's no tricks that we can play there. I think we're always limited to the classical communication speed. Separately with communication, there are really interesting ways that people are exploring now in the lab to use kind of hybrid classical and quantum computing methods, but that's different than kind of harnessing this speed of light story.
I would only add that I don't think there's any way to use the entanglement to do anything you couldn't do with classical speculative computation. You want to do the teleportation? You want me to?
No, go ahead. Yeah.
All right, so let's teleport something. The basic idea with teleportation, it's another one of these things that was discovered by a dude named Charlie Bennett, who is a researcher at IBM. Did I miss something there? The idea is to move a quantum state from one place to another. So when we're talking about teleporting something, we're not talking about physically taking this camera or this table or something and having it reappear in a different place. We're just moving the information that represents it from one place to another in the quantum context. So that's Charlie, and this is the particular paper. Dates to 1993, and it was actually demonstrated experimentally not too long after that, fairly quickly, by a couple of groups. Let's see, so what is it? We got Alice and Bob. Alice has a qubit, a data qubit, so we'll label it D. And the idea is that Alice wants to take that quantum information and send it from where she is over to where Bob is. Okay. Sounds nice, right? So how are we going to go about doing that? What we're going to need is we're going to need these Bell states again. We're not going to go through the math in this particular part, but as we noted earlier, you can treat these as a basis set that will fill any two-dimensional space with complex numbers. And we take advantage of that fact in the teleportation operation. So we start with a single qubit, which is in some state that we don't know. Maybe it's something we prepared, or maybe it's something that somebody else prepared and gave to us. We don't know what it is. As we already noted, so for example, with this single qubit, you've got alpha is your quantum amplitude for the state 0, and beta is your quantum amplitude for the state 1. The probability that you'll measure alpha or measure 0 is the absolute value of alpha squared, and the probability that you'll measure 1 is the absolute value of beta squared. And on the right and at the bottom, you can see what happens when you perform some simple operations on this that we call the X and Z operations. I'm not going to go into the details of what happens with those, but those are two basic operations on a single qubit. Now, so what happens? Alice has this qubit, she wants to get it to Bob, so what she does is she begins by creating one of these Bell pairs. She takes this and, well, sorry, not, in this case, in this diagram, we're showing them being created here in the middle. So somebody else, a third party, is creating this, quantum Bell pair, two qubits we call A and B. We take those, we distribute them, one to Alice and one to Bob. So Alice now has two qubits, the data qubit that she wants to send to Bob, and this A qubit, which is a generic resource. So this is something that, that the network can make and that is used for doing this teleportation. She takes her qubits and she performs what's called a Bell state measurement, which is a joint operation on the two qubits. It's not the same thing as measuring the two of them independently. But when she does this, she's going to get 2 bits of classical data out of it. In this case, is 0 and 1. And she has to send those to Bob, who then takes those values and uses them to apply either a Z gate or an X gate or both to this qubit. And that recreates the state D that Alice started with originally. So it's moving the information from this. And note that even though in this diagram we drew A and B and coming from one place and spreading out, there's not even a requirement at the mathematical level that these be the same kind of physical qubits. So D could, on the left, could be the state of one of the ions in Tracy's laboratory, and D on the right could be the state of one of the superconducting qubits in Yorktown, if we can figure out how to connect those at the physical level. The mathematics supports that. All right, so implementation stuff.
I think it's a good break point.
I think we should take a couple minutes break. What do you all think? Who wants a break? All right, let's see. It's 5:03. Restart at 5:08. 5 minutes. That should be enough time for everybody to walk down the hall and back. Restart at 5:08 sharp. Stand up, stretch, and then we'll restart. Restart. Who has come up with questions over the last 5 minutes while chatting with their neighbor or otherwise circulating blood a little bit more closely? Somebody stuck a hand up. Got a question? Come ask your questions, and then we'll go from there into implementations. Oh, we got actually several people. Good.
Yeah, Tim Chen. So I think you said in the last bit there that you take the bell pair, one part goes to each party.
Yes.
There's some computation or mutual observation that happens on the left side, and then some classic state bits, or some classic bits are sent, i.e. normal data bits, is that to the far side?
They are two data bits, two classical data bits that get sent left to right, yes. As it happens, because of the way the operations that Alice performs, those 2 bits are guaranteed to be completely random. So there's no way you can predict what they're going to be. Alice just measures them and gets 2 random bits, sends those to Bob, and he uses them to finish the reconstruction of that D state.
Okay. So how much, is there just one, essentially, how much state is there in what you've then moved? How many bits of state?
1 bit's worth, yes.
So
and
you
it takes
use
2 bits,
two bits to
takes
generate
2 bits
one
to
bit.
reconstruct it.
Okay,
yes.
that's where I kind of got confused. All right.
So state your name, let's see. Yeah.
Marie-Josée Montpetit. Actually, the way I see it, this looks a lot like information theory. What you do is you take an amount of information, you do a known operation on it, you send that operation result over the network, and at the other end, because you know in combo with code was used, you transform it back. Is that a good analogy?
Would you say that quantum computational or quantum information theory, is that just like classical information theory with complex numbers?
So I think I don't know enough classical information theory, but I think that's in my understanding, that's a pretty reasonable description.
Okay, so then I understand what's going on. Thank you.
Yeah. There's a guy named Mark Wildy who's a professor at Louisiana State University who has written about a 700-page book on quantum information theory. It will stand as one of those classic books, but trust me, it's not an easy read. Yes, state your name.
Hi, Robin Wilton. I think I can guarantee I won't be sitting down and saying, hey, yeah, I understand this now. But my question is that in the presentation so far, it seems to me that you have treated quantum computing and quantum entanglement as essentially the same thing, because you've only talked about quantum computing and distributed nodes. Will you be talking about quantum computing on single nodes at any point? Or is that something I should just go away and read about?
Not quite sure I follow the question, so
Okay, it was as dumb a question as I thought. I'll go and sit down again.
No, it's fine. Go ahead. So yes, we're talking about.
It feels to me like you haven't talked about quantum computing except in terms of quantum entanglement.
So far, yes, I think that's true. That's true.
So I guess I would say on one hand, by focusing for the tutorial on quantum networks and quantum repeaters, we're sort of putting quantum computers to the side. We might want to use them, but they're not the focus, because there's something that would happen at a single node and they wouldn't be distributed. In general, I think we can make the statement that entanglement as a resource would be something we would expect that you need for a quantum computer. Okay,
thank you. Yay, I understand this.
Good.
He lied fluently.
Suzanne Wolf for the Jabber Room. Could you repeat the name of the book you just mentioned?
The name of the book, the professor is Mark Wilde, W-I-L-D-E, and what's the name of the book?
I don't know.
I think the name of the book is just Quantum Information Theory. It was published, in 2012, give or take, yes. I think, around through there? And it's about 600 or 700 pages long. I'm not sure how you pronounce it, Wilde, W-I-L-D-E. Pretty easy to find. All right, I guess that's it. You're up for the hardware stuff, implementation stuff.
Hi, yeah, so as I didn't mention earlier, I'm working at the Institute for Experimental Physics at the University of Innsbruck, and I'm the hardware person here, although I don't usually think of it as hardware. I think of it as atomic physics, in in this audience, I think that's what counts as hardware. So let's think about how I can make my own bell pair. And what we want to remind you, we want to come back to this idea of a quantum system with 2 levels and encode information in those 2 levels. So we kind of look out in the world and we try to find systems where we would have these kind of 2 levels, 0 and 1, where we can have these amplitudes that Rod sketched out mathematically. And then we start to get picky and we say, well, we don't just need a system with 2 levels. What else do I want? Well, my quantum bits should be something I can entangle with one another in some straightforward way. And we've also heard that you want to be able to measure those quantum bits, and actually in different bases. So you want to be able to perform these different measurements. That is, you want to be able to change the phase in which you measure the quantum bits. In this description where we said we can describe 2 quantum bits in a basis of these 4 bell states, we want to be able to measure them in all of the different bell states to project them in this linear algebra picture onto one of the 4 bell states. And both entanglement and measurement, we want those to be fast and we want those to be accurate. And we don't want to be losing information to our environment. So we've drawn this very beautiful formal picture where we only talked about the quantum states. And that's assuming that we can isolate those quantum states from their environment. But you should kind of keep in mind that in that sense, entanglement and measurement are sort of at odds with each other, because in this beautiful space of entangled things, we want to keep everything as far away from the rest of the world and only have those states. But as soon as we talk about measurement, this is an interaction with the rest of the world. So we need to protect them, except when we don't want to protect them, and then we need to be able to measure very fast. Right, this interaction with the environment can cause what we would describe as decoherence. It would create what we've heard from Rod as a mixed state. It reduces what we would describe as the coherence between these different parts of the quantum state, which again you can think of in sort of as a phase relationship between waves. So it's nothing mystical, it's just this wave picture here, and you want to establish a definite phase relationship, and when you start adding other systems into the picture, you lose that phase relationship. You might also like to be able to move those quantum bits around, especially since we're talking about networks. And this might be obvious, but actually maybe not in this community, where you also know that as you make your hardware smaller and smaller, you run into very physical defects. And so it's a very sensible demand that one qubit should be like another qubit, that we want to not have to deal with the idiosyncrasies of individual qubits. So yeah, this I actually used an abbreviation that I got rid of earlier here, and I actually mean 2-level system here. So, and I tried to get rid of that for lack of confusion, and I failed. So, 2-level system referring to these quantum mechanical 2-level systems. And so, yeah, there are many different possible platforms, and it's going to depend on your application. So, photons. This is a great idea. Why? Because we have this huge resource of optics as an industry. We can buy lasers off the shelf. We have lovely optical fibers, wave plates, detectors. So it's a very a relatively straightforward thing to set up these kind of optics experiments in the laboratory. But when we want to store quantum states in photons, we kind of start talking about photons as individual objects, and it becomes a little bit tricky, or more than a little tricky, to work with one and only one photon. And so that, is a challenging story that one could talk about for a long time. Also, yeah, they're always moving, right? And so there might be times where we're drawing these sketches of quantum states for you, and you want to say, put a quantum state in a box and have it stay there. And for photons, the only thing you could do is have it run around in an optical fiber, and eventually the losses in that fiber are going to start to catch up with you. Atoms. Okay, so if you want things to stay in one place, atoms are nice for that. And we also have a lot of tools with which we can manipulate atoms. We can have very precisely controlled interactions between the electronic states of our atoms, using lasers or using microwaves, depending on the particular atomic transition. So here the 2 levels would be about choosing different electronic states. We can use these atoms for storage and processing. So we can not only map states onto the atoms, but can very precisely store and manipulate information within them. I would say these are more sophisticated experiments than with photons in terms of the hardware that's required, in terms of the cost. And this is a plus or minus. If you don't want them to go anywhere, if you want to sort of build a quantum computer on a tabletop, this is great. But if you do want to transport them, now you would be talking about sort of picking up a vacuum chamber under ultra-high vacuum and carrying it around, which sounds very impractical. And a third very broad category one can describe as artificial atoms, things that we fabricate, for example, in a clean room that should, behave like atoms, but where we can maybe take advantage of the tunability that we have. So examples here would be vacancies, so defects in diamonds, or quantum dot systems. Also what's known as superconducting qubits that are based on Josephson junctions, and they interact with microwave cavities. And all of these systems have properties that can be readily tailored, and we can take advantage of capabilities for very scalable fabrication from decades of industry here. But this brings us back to questions of, are these systems really identical with one another? Now that we're fabricating things, if I have a cesium atom, I can believe that it's going to be identical to this other cesium atom that I can find. But this gets a little bit more challenging here with these artificial atoms. Also, the multi-level structure that one can fabricate becomes a little bit more complicated. Again, the artificial atoms we can think of as very localized in space. And so this brings us back to the slide that Rod showed at the beginning of our tutorial, this diagram from Jeff Kimball's 2008 Nature paper, where he was picturing this idea of quantum nodes of a network and quantum channels. Because you can imagine that both of these capabilities are really important. On one hand, to be able to store information in quantum memories, maybe to process them at quantum computers, and those are all things you would like to be happening at a node in space. But in order to transport quantum information, photons really seem like a very clear choice here. And so this also maybe comes back to the first question that was asked in the first half of the tutorial about the role of distance, because we can think about, if we want to make bell pairs, what does it mean to make a bell pair? And if we're making a bell pair at a single location in space, and then distributing that bell pair over space, then we have to think about how we can distribute it with the minimum loss. Okay, I want to give you kind of one slide on each of these pictures on photons and atoms. So just to briefly give you the sense of how we could encode 0 and 1 in a photon. Well, we can use polarization, so we could take advantage of photons having this property of having two orthogonal polarizations. We can use time bin encodings. Did a photon come early? Did it come late? And sort of identify two discrete time bins. We can also encode it in the number of photons, and 0 and 1 would typically be the numbers that people use. So either I have no photon or I have one. And the final one that people often use is a path, having two different paths and saying, did the photon go left or did it go right? This is a picture from Jeremy O'Brien's Science Review article back in 2007, just kind of some sketches where he depicts certain aspects of this encoding. So here you see in the upper left-hand corner a sketch of the two orthogonal polarizations that you could use for a polarization-based encoding. And then the question of how you would do gate operations that Rod described on your quantum bits here. So in this case, one could use wave plates. This is what's depicted below. If you can use half wave plates and quarter wave plates to rotate these photons, and those are single qubit gates. Those are changing the state of a single qubit. And then in the fourth picture, it's actually a picture of this kind of path story, or actually converting between a polarization encoding and a path encoding. So there are lots of interesting techniques for manipulating these photons as quantum bits. And then just a kind of a glimpse at this idea about atoms. So you want to, you have a whole periodic table to choose from, and you want to think about two electronic states that would be well suited for a qubit. So you want to think about what the lifetimes are of these states. You certainly would want to have the both of the states be relatively stable. They don't need to be infinitely stable. And can you manipulate these states easily? For example, with lasers that are available off the shelf, or with microwaves that you can kind of dial in the lab. Maybe these states are particularly robust with respect to environmental fluctuations, and that would be certainly a plus. So this is just a picture here of, this is on the right-hand side, what's known as a linear Paul trap that we use in my group and in many other groups around the world to trap ions. So under ultra-high vacuum, we apply radio frequency to these electrodes of this trap, and this provides a potential well in which we can trap strings of charged particles. And if we can use lasers to cool these particles, then they actually stay in these traps for days, or even up to several days or weeks, depending on the conditions and the species. This is a really beautiful camera image from Rainer Blatt's group in Innsbruck, where they've really pioneered quantum computing research with trapped ions. And so this is about, I forgot, I counted once, it's something like 50 ions. And we're looking at fluorescence from those individual ions. They're repelling each other because they're all positively charged. They're all calcium ions with a single charge. So on one hand, they're kind of pushing each other away, but on the other hand, they're all sort of being trapped at the same time by the radio frequency voltages applied to this trap. So we get this kind of string, this register of ions that one can use potentially for computing, or also for networking capabilities. Okay, so let's get back to this plan of making bell pairs. And how would we generate remote entanglement? And so this is, I'm going to kind of sketch out a couple of ways you can do this. This is an idea of how to do this probabilistically. And one idea would be that you have two atoms here, which again could be these artificial atoms. And you could have each atom emit a photon. So that's what you see in this upper left-hand corner picture. The atom at node 1 and the atom at node 2 are both emitting photons. And so there's a couple of variations here. One variation is either the atom emits a photon or it doesn't. That would be what we call a number state encoding of the photon. And we could say that we could engineer it so that the atom state depends on whether or not it emitted a photon. If we use a polarization encoding, which is actually what you see below, it should say C instead of B there. If you use a polarization encoding, instead of the photons, the state depending on whether or not emits a photon, instead it will depend on what the polarization was. But the key aspect in both cases is that the photon is detected. Here it's a single photon that's detected. In the sketch below, it's two photons that are detected. But the most important thing is that the detectors can't tell which atom generated which photon, or if it was a one photon, which atom generated that one photon. And that lack of distinguishability, that indistinguishability, means that the detection event actually projects the atoms into an entangled state. So we would say that this act of measurement prepares an entangled state between these two atoms. So that sounds actually kind of easy. You can kind of get each of two atoms to make a photon, and you need to measure the photons, and then they sort of turn up entangled. And yeah, this is, again, as I said, the key principle, this indistinguishability from the perspective of the detectors. And so the first experiments on this really pioneering experiments, were done at the University of Maryland, or actually originally at University of Michigan, and Chris Monroe, who's the principal investigator, is now at the University of Maryland with the Joint Quantum Institute. And he, in a series of experiments for kind of more than a decade, he's done exactly this. So here's a picture of the kind of ion trap that they use in their system, where it's sort of a more complex version of the radio frequency trap that I showed you earlier, where they can apply, again, radio frequency voltages to this trap in order to confine ions in this very small space in between. And actually, they have two different traps here in this. This is a picture taken from their 2015 paper, where they have traps separated by a couple of meters. And in each of these boxes, they're achieving ultra-high vacuum conditions, that are 12 orders of magnitude, 13 orders of magnitude lower than atmosphere. In one of their vacuum chambers, they have 2 of these atoms, and they're ytterbium ions in both cases. In the other, they have just 1 atom. And so they pick 1 atom from the first chamber, 1 atom from the second chamber. Each atom they manage to entangle with a photon. Those photons go onto a beam splitter here to erase information about the direction that the photons came from, and then they measure the photons at the end. And this is just sort of a picture that shows the electronic states for these atoms. And so the important thing for us is that basically that they are able to choose 2 different electronic states, the left one here and the right one there, and those they can identify with their quantum bit. And then they have a scheme where they use a laser to excite the atom, and it either decays in one direction to one state or in the other direction to the other state, generating different polarizations. And basically they can do some measurements. I'm happy kind of later on to go into the details of what it means, but they can characterize their system in such a way that proves that they have entanglement. First, they can show entanglement between the atoms and the photons, and then this is actually the basis for their entangling the 2 remote atoms here. So these are measurements that show that the atoms are entangled with one another. And Rod already mentioned this idea of a state fidelity or a fidelity. And again, from a linear algebra point of view, you can just think about that as a projection. So they're in this Brockett notation, they're multiplying the ideal state with the experimental state. And if it's perfect, if the experimental state is the ideal state, the fidelity is 1. There's a classical bound of 50% for these. And so, they're not perfect, but they have really clearly non-classical states. And I also want to give you a sense of the rates in these experiments. This was an experiment where they were generating entanglement 5 times a second, 4 times a second. And that was an improvement of, I think, 8 orders of magnitude.
Something huge, I remember
So they had from their 2007 paper. So on one hand, we have just incredible improvement over the course of a decade, but in terms of rates that you can then use to generate one-time pads, we're still a long way off. So that's a story about ions, which are the things that I know best experimentally in this context. But over the past decade and a half, there have been examples of remote entanglement, very similar experiments sort of demonstrated in a handful of different settings. And also in a few of these, not only remote entanglement, but also teleportation has been demonstrated. So in this picture I showed you here, we had the 2 quantum bits above and the 1 below, which looks very similar to the picture that you saw from Rod, where you can then use the entanglement between the pair of the 1 above and the 1 below in order to teleport a state between the 2 chambers. That's been done with the ions, with neutral atoms. It's been done with superconducting qubits, and we actually, I think, not the ensembles, but pretty much at least 3 of the systems here. What I also want to emphasize here is that the state of the art yet now consists of 2-node experiments. And really kind of, maybe 2 systems over here on one side and 1 system over here, where I'm limiting myself to a discussion of things that are really physically separated. So, there's been a lot of progress, but, and we're looking forward, we know that we, as a community, really need the kind of help of people thinking about networks, but we don't yet have those networks in place. So we're optimistic that these are coming quite soon, but the kind of 2-node connections are what people are doing right now. And I think that brings us to repeaters. So I'll hand it over to Rod.
Yes.
If I could, there is a question in the Jabber room. Why doesn't the detector measurement destroy quantum state rather than create entanglement?
Sorry, read that again.
Sure. Why doesn't the detector measurement destroy quantum state rather than create entanglement?
Yeah, you want to take that?
So why doesn't it, right, destroy? Yeah. So something gets, it's interesting, right? Something gets destroyed. So at the start you had an atom and a photon, say, over here, and you had an atom and a photon over here. And you measured the 2 photons, and the measurement was destructive. So the photon state the photons are gone. They were absorbed by your detector, and they're lost. And also, the entanglement that you had between the atoms and the photons if you know, that's lost. There are also schemes that don't rely on entanglement, but if it was a scheme based on entanglement, you've lost that entanglement. And so, yeah, you did get rid of something in your measurement, but you also were able to harness this indistinguishability in order to create entanglement.
Yes.
Dave Wheeler, one more question. So you talked about the rate at which entanglement was happening. I think you said 5 times a second or something like that, and that's an improvement. What is the sort of speed or velocity that we're at in actually improving that and getting to the point where we can get thousands of qubits or tens of thousands of qubits entangled? And is that something that is on the horizon, or is that something that we still see as several decades away?
So I think it's on the horizon, but kind of putting the different aspects together is certainly tricky. So I think Chris Monroe could give really convincing arguments of how they think they can get to 10,000, say, 10,000 events per second rather than one. In my group, we're going in a different direction. We also think we should be able to talk about kind of kilohertz rates. But yeah, and then you can get more speculative about how you keep scaling that, but it seems like first you want to kind of get that improvement. Additionally, having long, thousands of qubits separately, that also seems very promising, but then combining these different improvements can also be a challenge. Or, for example, there are ways that extending the this so-called coherence time that is reducing the interaction with the environment. That's also something that there are clear pathways for how to do. But certainly for networks, you want to put together all of these improvements at the same time. Yeah.
Right.
So
okay.
I would say it's promising, but also not easy.
Okay, thank you.
All right, let's see. So a couple of quick things that I forgot to mention right at the beginning occurred to me while Tracy was talking. Number one, the slides for this are up in the Data Tracker website. I uploaded them in both PDF and PowerPoint format, and both of the files are kind of large, so tens of megabytes, unfortunately, because of all the pictures and whatnot. There's a huge appendix in this. We're only using about half of the slides of this, and there's a huge appendix with a bunch of the math in it. So if you want that, you can get it and take a look through that as we go. And second, while Tracy was talking, I looked up, yes, the title of Mark Wildey's book is just Quantum Information Theory. Keep in mind that that's an information theory primer or textbook, not an introduction to quantum computing, and certainly not an introduction to quantum networking. So if you like classical information theory, you'll like that book. All right, so we saw this earlier on. What's the job of a quantum repeater? It's to make this base level entanglement over a link, which is what Tracy just talked about. The ability to couple entangled links along an end-to-end path to meet the application's needs to build that, to monitor and manage the errors, and to participate in the management of the network as a whole. So what do we have? Well, conceptual hardware, you've got a series of nodes, and each one has inside of it some set of stationary memories, a qubit, which I've drawn using the atom symbol here, and these stations are separated perhaps by tens of kilometers. They're not separated by thousands of kilometers, generally speaking. They're pretty short distances as we go. So how do we build entanglement from one end of this chain to the other? That's what we're trying to accomplish here. There are also all optical approaches to doing this with no stationary memories at all. We're not going to talk about those. They have their own set of challenges. They're pluses and minuses, but we're just not going to talk about them today. All right, so ideally what you might like to have, and what everybody in this room probably has in their head, is a store and forward architecture, right? Where you're taking a qubit and going hop by hop across a series of hops. Unfortunately, that's not going to work. Why? You take those individual photons and you put them in a fiber and you lose them. And you do it again and you lose it. And then eventually maybe you succeed in getting one through the fiber here end to end. But the loss in the channel is always going to be high. It's always going to be too high to actually encode information and put this on it. Well, always, for a very long time now. We'll talk just a little bit about that later. So we have to find some way of dealing with this tremendous amount of loss in this. Okay? That means we're going to wind up using some sort of acknowledged link layer. Axel Dahlberg, who's around here, Axel, stick your hand up. So Axel's over there. He's from Stephanie's group. He gave a presentation in Bangkok on some of their hardware roadmap stuff, and he also has an internet draft on a protocol for link architecture stuff, and we're going to talk about that tomorrow during the meeting. But you need to essentially build an acknowledged link layer in order to make this whole thing work. We can draw this sort of time-wise and sort of with time going down the vertical axis, top to bottom, and distance going left to right there. We can draw this as sort of a gray trapezoid, something that looks like that. If you put a bunch of them together, you might imagine stringing them into a series of things like this, and maybe we can acknowledge them as we go and do sort of hop-by-hop teleportation, even though we couldn't really just put it on an individual photon and send it from one place to the other as we go hop-by-hop. Maybe we can do teleportation hop-by-hop. The problem is this takes long memory lifetimes and the fidelity of the operations. The probability of success in doing this is insufficient for this to work over more than a couple of hops. Right? So the group in Delft is building a network with a couple of hops, and their first implementations may in fact do this or something similar without applying some of the error correction techniques we'll talk about. But if you're going to extend beyond that, you're going to need these kinds of things, and you're going to get into these generations of repeaters here. So loss error, again, defines how you do things at the link level, and the operational errors and dealing with those is how we is going to have to be dealt with end to end as we go. So very quickly, several different repeater schemes have been defined. I listed 5 of them here. That paper that I just showed you from Murali Durand and from Lang Zhang's group, they defined essentially 3 generations of networks. I call them 1G, 2G, and 3G. 1G uses what we call purification and uses what we call entanglement swapping over acknowledged links. This is truly a distributed computation. This is not store and forward. This is not simple data plane stuff like you have in a classical internet router. This is end-to-end a distributed computation. Okay. 2G is, all right, let's do something more sophisticated. Let's apply error correction to this over acknowledged links. And then it does become a little bit more akin to store and forward. But really you get into that when your success probability for doing this gets to the point where you can live without the acknowledgements on the link layer, and then you can do what's called a 3G network for doing this. Right? So this first generation, this quantum repeater operation, I've got 3 stations here, 0, 1, and 2. One has 1 qubit, station 1 in the middle there has 2 qubits. So what we do is we use the link to make entanglement between station 0 and 1, and we use the other link to create entanglement between station 1 and 2. And then we execute, again, one of these things, Lebel state measurement. This operation is very much like teleportation. You could, in fact, consider it to be a form of teleportation. This destroys the 2 qubits in the middle, but it doesn't destroy the 2 qubits on the end. And if this works properly, what you're left with is entanglement between the 2 endpoints. This process is what we call entanglement swapping. Now, unfortunately, this does introduce errors. It reduces the fidelity of our system, and so you're going to have to apply some error management techniques on top of this. But this is the key technique to get beyond a single hop. This is what you have to have. I did not draw it on this particular slide, but in order to make this work, you have to have the corresponding classical communication, just like we had with teleportation. You do this repeatedly over a set of what you might call nesting levels. So level 0, you're building entanglement over individual hops, and then you do this entanglement swapping once at your odd numbered nodes, and that takes you from, in this example, from 4 entanglements over individual links to 2 entanglements over two hops, and then you can do entanglement swapping again at station 2, and you've gone from 1 hop to 2 hop to 4 hop entanglement as you go as you're doing this. And again, there's a tremendous amount of classical supporting communication that has to be done for that. But this introduces errors. So how are we going to deal with this? The standard technique, which people have actually begun to demonstrate experimentally, is what's called purification. I think Tracy's going to talk about that here in just a couple minutes. This purification is a form of error detection. This is not error correction. This is error detection. And what we do is we start with two sets of bell pairs, and we use one of them as a test tool to test a proposition about the other one. And so you use that and you do some local operations at your stations at each end. And if everything goes well, what you're left with after this all runs is the test tool has been destroyed, but it has given you some information about the other bell pair or the other entangled state that you have. And in the case where this test succeeds, it increases your confidence about that remaining bell pair, and you have said, with higher probability, we believe the entangled state is actually good. So, dealing with all this, you could call this, we can define this in terms of a protocol stack. You're going to have physical entanglement at the bottom, and what at the time I called EC, the entanglement protocol, the entanglement control protocol, back in a paper we had in Transactions on Networking 10 years ago now. Wow, 10 years ago, wow. And then you have some software that will do purification control, and you got some protocol that will do entanglement swapping control, and then maybe purification control again, and then ultimately application on top of this. Note that these two here at the bottom, they operate over distance 1. The others repeat at different distances. So you're doing entanglement swapping over 2 hops, and then 4 hops, and then 8 hops, and then 16. You also have to repeat the purification, because at each level where you're doing this, you're introducing new errors. And then ultimately, finally, hopefully one purification end to end, and then the application level all the way at the end. Note that the only quantum part of all of this is right there at the bottom. Everything else above that is classical networking stuff, and that's why everybody in this room is needed to actually build this. Because when you put this together, as I said, these things are a true distributed computation. Right? You take this, even over 4 hops, you're going to have a complicated set of interactions between the 4 hops for managing these. Some of the operations over 1 hop, some of them over 2 hops, some of them over 4 hops as you go, some of them you're the end-to-end as you go. All right, so 2G and 3G, so that was 1G networks. 2G and 3G are still very far away. Even 1G is very hard. You've probably gotten an idea from what Tracy talked about. The entanglement success probability is low. There are many round trips involved in the protocol design. You've only got a few qubits per node. The memory lifetimes are still problematic. And when you want to do entanglement swapping, getting a successful entanglement between Alice and Bob at the same time that you have one between Bob and Charlie in order to make that entanglement swapping, that's one of the current challenges experimentally for what people are actually doing. 2G is going to blow up the resource requirements by an order of magnitude, give or take, and the biggest problem that we have besides that is in the existing quantum computers and in the laboratories. The operations themselves are not yet good enough to make full-on error correction work. We're actually getting close to that, but we're not there yet. For 3G, not only are you going to have error correction that works and a lot of memory in each one of these nodes, but you're also going to have the probability of 80 to 93%, depending on your choice of code, in getting every single photon you put into the fiber out the other end and detected properly. And what are the current success rates in your laboratory for actually detecting a photon that comes out of an atom?
Between 5 and 10%.
Between 5 and 10%?
Yeah.
That's actually really good. That's several orders of magnitude better than it was just 10 years ago, right?
But right, the detectors okay, these days you can buy really nice, expensive superconducting detectors that get you very close to 100%, but for a long time, the detectors themselves were 50%. And for telecom, it's worse. So yeah, so then right, you're already kind of killed with just the detection step. So that's a very new thing that the detection step doesn't kill you right away.
So you got to get from there, from this 5 to 10% she can achieve in the lab today, to 80 to 90% success rate in detecting every single photon. So those 3G networks, which would be real store and forward networks, the same way the data plane on the internet runs today, those are a long ways away. All right, let's see. You want to do this bit?
Sure. So this is really fast because it's the perspective on experimentally where we are on these repeaters. And yeah, we're not very far. And so I'm just going to kind of capture that for you. And we're going to kind of have a little recap of what these repeaters were looking like. So, so hopefully it's a quick reminder. So we think about, when we hear from theorists, as experimentalists, when we hear kind of from theorists about this second generation and third generation, it's very interesting intellectually, but you're also kind of like, really, are you kidding? So, 1G, it looks from our perspective hard enough. So what would that look like for these ions? Well, what you would do is entangle one pair of ions in the same way that I've already showed you. So you would have a single ion here, for example, that gets entangled with a photon, a single ion that gets entangled with another photon on the right-hand side, and then this beam splitter is supposed to show you that we're erasing the information about which path each photon came from, and then there's some detectors that I left out of the picture. So you would entangle those two ions on the left, and you would entangle the other two ions on the right, and then you would do this Bell measurement that Rod talked about on the two central ions, and that Bell measurement would then entangle the outermost two ions. So I haven't given you any sense of how we do this Bell measurement in practice on the ions. Maybe I can try to kind of give you the 30-second version. The key is that we think because these ions are on the one hand repelling each other and on the other hand trapped in the same trap. You think about them, like we would describe them as a coupled harmonic oscillator. They're kind of pendula and they're coupled to each other and they're swinging together. So their motion is linked to one another. They have shared motion. And we can use this, what we would talk about as a motional bus. So we can, on one hand, we have access to the electronic states of the ions, and on the other hand, to their motion. And we take advantage of that in order to manipulate the joint states of the ions. So we can do measurements, we can project the state of these ions into one of the 4 Bell bases. And what we do in the end is we illuminate the ions with certain laser light, we look at fluorescence, and based on those fluorescence measurements and our manipulations with lasers, we can say, which one of these 4 Bell states are the ions in. Okay, so this Bell measurement on the ions in the middle then entangles the ions outside. So this is, if you're still awake after a couple of hours and a long day, you learned already that this is what's called entanglement swapping. And it's really nice, and so our tendency is to start to chain together a bunch of these things, but this is an approach that's not scalable because these errors are going to accumulate. All of these steps will have intrinsic errors, and when we start to concatenate things, it's going to go downhill. So the approach would be entanglement purification. So what we should remember is that this idea of a quantum repeater, at least in the first generation, you think of it as entanglement swapping plus purification. And the key concept of purification is that you have multiple copies of entangled pairs, which allow you to, then you can start sacrificing some of your copies in order to get a higher fidelity. And you need to be able to do gate operations between pairs of local qubits. So here's again, I'm trying to think of a minimal instance where you could have not only entanglement swapping, but also purification. So that now let's think about an instance where we double everything. So we have 2 ions over here, 4 ions in the middle, 2 ions there, and then we would entangle these 2 pairs of ions. So pairwise entanglement on the left, pairwise entanglement on the right. We would do 2 Bell measurements here, and then we would have 2 entangled pairs between the left and the right-hand side. And then would come this final step of the purification. What we would do is we would do what's called a parity measurement of the ions. We would ask on the left-hand side, are the ions both in the same state? Are they in opposite states? And we would also ask that on the right-hand side. Then we would have classical communication to share that information. And based on the joint outcomes, we would either throw away the pair, or we would, if we got the outcome that we liked, then we would know that the purity had sort of had increased, or at least the chances that that we have a highly entangled state has increased at the cost of sacrificing one of those pairs. So we do a measurement that sacrifices one of our 2 ions on either side, and in the end we end up with a pair that's more highly entangled. And so you can show that this would then be a scalable thing. With the purification, if you can meet certain bounds, you could then start to concatenate these systems.
questions?
Yeah, so I'll just finish the
Okay.
slide and then go to the question because I think this is the simplest story. So in a nutshell, repeater is entanglement swapping plus purification. We have to wait for classical information to travel. And the simplest version would be what I've sketched here, 8 qubits, 3 nodes, and you need these gate operations. So nobody's done it. That's what you should take away. People are working really hard. I think it's quite likely that in the next 2 or 3 years, we'll have a kind of a first proof of principle experiment. The closest experiment so far, I wish I could tell you it was with ions, but it's actually with nitrogen vacancy centers and Ronald Hansen's group at Delft. So these diamonds where you replace one of the carbons with a nitrogen, and they've done purification of entanglement with 4 qubits. So in beautiful experiments there. Maybe I'll pause there. So that's the end of the experimental story on where we are with quantum repeaters, and maybe go to the
Yeah,
question.
I think you may have answered my question, but go back to the first slide where you just have single dots, not pairs of pairs. So is this ion entanglement a single qubit being transmitted?
So at this point, there's nothing that's been transmitted. What we've done is we've generated remote entanglement, which you could then subsequently use as a resource for teleportation.
So is this entanglement property a single qubit that's going on here, and then it's... Because what I want to know is if you need to send or want to entangle yet another one, is it done serially? But your subsequent slide shows it could be done in parallel.
It could be done in parallel, and that's a very, So here what you end up at the end with is a single bell pair of 2 remote qubits, which you could use to teleport a single qubit. And then here I sketched something in parallel, and that's really platform dependent. So I would argue that ions are a nice system for doing this kind of thing in parallel, and it will depend on the system how well you can parallelize it.
Hi, Juan Carlos Zúñiga. I was a little worried when I saw the diagrams of the protocol stack and the Gs, and kind of remind me my nightmares about 3GPP and SA2 and things that I don't want to feel and live here. But I was even more worried when I started thinking, disruptive ways. Like in this repeater, is there a way that you can start foreseeing that there will be attacks of a man in the middle? Is it possible to split the state so that you can have someone sneaking in, and then even though these 2 nodes are entangled, there's a third one getting the state?
So actually, I would say this is something we don't have to worry about, because somehow that a measurement in the middle by a man-in-the-middle attack, it will compromise the entangled state so much that then when we try to purify, it just won't work. I mean, so the bad thing that can happen is they can kind of a man in the middle could prevent you from building up entangled pairs, but you won't be able to, someone won't be able to compromise your security.
So that's part of that's dependent on the fact that we actually are doing more of the checks end to end, and so those end to end checks will determine that the kinds of states that are left after these operations are exactly 2 qubit entangled states. If somebody, for example, the man in the middle tries to sneak in and entangle a 3rd qubit with it, that shows up in the statistics for the tests that are actually done end to end. We can prove that this isn't a 2 qubit entangled state. We might not know for certain whether it's 3 qubits or whether it's just been busted and we don't know what the problem is, but we know it's not a good 2 qubit state. And conversely, we know when we do know that we have them, we know that the path is working end to end, and it doesn't matter what's happening in the middle.
And it's always 2?
Yes.
Okay, thanks.
Actually, for that security guarantee, you
name,
need
please?
Scott Fleur. For that security guarantee, you have to make sure that the classical bits that you are actually sending back and forth, but you don't show, have actually been authenticated. But that wasn't my question. My question was really about how many purification steps you need to do for each round. Is that it's obviously going to be somewhat fixed based on how good your physical layers are, how error-free they are. But how many times do you have to expect before you get good enough to be able to go up to the next level?
It's actually a really good question. I would say go read my transactions on networking paper from 2009, and that will actually give you, I think, a good framework for how to think about that. But that particular paper was built on top of a simulation of a particular type of system that nobody's really trying to build anymore. So the specific numbers that are in that paper, I would say, are outdated. Do you have something more about the current stuff?
I mean, I guess what I would think about is work from Simon Benjamin at Oxford, where they've looked at very sort of state-of-the-art fidelities for ion photon entanglement and shown that those are kind of reasonable for scaling. So I know that they maybe have numbers there that I don't have in mind about how many purification steps, but absolutely. So the better your states are to start with, the fewer steps you'll need, and if you have really, states that are quite close to classical, you would need sort of a prohibitive number of steps.
I'm trying to think is a similar question, is how do you know how much fidelity you need if you're applying the purification to improve it? And if you make fewer copies essentially with higher fidelity, how much fidelity do you need in order for this to work reliably?
My group is putting a paper like that out in preprint form sometime in the next couple of weeks.
And is there actually a definition of fidelity when you?
It depends in part on what the end-to-end application is that you're trying to do. For QKD, it's actually pretty low. I don't remember what the number actually is.
So QKD would be the one of more practical interest now, I think.
But if you want to do real distributed computation, you need high 90s of fidelity, and so that means not only that your hardware has to be really good for the purification that you're doing, but it also means that you wind up spending a lot of resources to do what's called tomography, to test the system to see how good it is. The better the system is, the more you have to test it to figure out what the error rate is.
Okay. These are the kind of questions that people are very much interested in right now, trying to understand them. Yeah.
So you're asking the right questions, right? Those are the questions we're trying to answer right now.
I'll take that as a plus. Thank you.
Separately, I have to benchmark my system, and then I want to do this, and I have to hope that it didn't change from when I benchmarked it, or how much do I have to interrupt it to benchmark it while I'm running it, and how much does that cost me in terms of resources? Yeah. So okay, with that outlook on what we hope will be demonstrations in the next few years of building blocks for quantum computers, I think we've got a couple slides at the end about the state of quantum repeater research from a theory point of view.
Yeah, so just real quickly, to give you an idea, I should maybe have couched this as what are current open problems and what we think are kind of solved problems, but I picked up just a handful of things from my own group and from Stephanie's group, which are two of the groups that are working on networking research as opposed to the physical layer stuff, just to give you an idea of what sort of things are, where things are. We have done some work on network architecture, based on Joe Touch's recursive network architecture, for those of you who know Joe. The protocol stuff that we already talked about a little bit. We've done some work on routing. We've done some work on multiplexing and control in larger networks. And we've done some work on internetworking. This was part of Shota's PhD thesis. If we had two different kinds of networks, how would we connect them together as we go from individual networks toward an internet? And we've done some work on the security of systems, what happens when somebody actually takes control of one of these repeaters. Do they have more capabilities than they would have in a classical system? We've done some work on resource analysis for applications, and we've done some work on the quantum equivalent of network coding. So that's sort of the range of things that people have been working on for the last few years. From Stephanie's group, Axel gave me this list of things. They've been working on link layer protocols and parameter regimes for dealing with this, and how you actually go about using this for particular applications, and a bunch of different stuff. They've built some simulators for doing this. That gives you kind of an idea of the work that's actually going on. And somebody has a question here real quick. Let's see, how are we doing time-wise? It's 6:02.
10 minutes.
I need a couple of minutes at the end of things to finish up, but we can do questions right now. Yes.
Have you done any tests?
Name, please.
Dino. Have you done any tests in low Earth orbit or geosynchronous orbit?
We have not, but actually we didn't include any slides from this, but there's been a community of people working towards satellite-based experiments for what, more than 10 years now. And they've done even some experiments in orbit saying, hey, maybe we could do some stuff with this. And then bang, 2 years ago, the team from China produced a really fantastic paper showing that they can generate two entangled photons in orbit and send them to Earth and detect those two photons and prove that they had entanglement at two ground stations 1,200 kilometers apart, was it, in China? Something like that?
Yeah, I think that's, yeah.
I was kind of begging the question, is the environment better in space than it is down here?
In a lot of ways, yes. So one of the most famous teleportation experiments, you want to talk about the Tenerife, do you know about what they've done?
Maybe just to say that, yeah, that there's been free space, really, I guess it was more than 100 kilometers, the Tenerife free space experiment. Yeah, and I guess I would picture those as having separate applications, that the free space or satellite-based experiments or satellite-based encoding can get you over these really long distances, right? Can get you global connections. But I guess we can think about applications where the connections will be so local, and certainly the resources of satellites, you're not going to have so many. Yeah, especially for things like maybe a more local distributed quantum computing, we would imagine that as being fiber-based.
Yeah, so that experiment was, about 10 years ago now in the Canary Islands,
Yeah,
right?
yeah.
They used two telescopes on two mountains 140 kilometers apart or something. And that, in some ways, is actually harder than going to a satellite, because 140 kilometers of air really distorts things horrifically, whereas if you're going vertically, you only got to go through about 10. But then you have to hit a satellite that's moving in orbit. And at the conference that Tracy and I helped run 2 years ago, we had a speaker who was the chief engineer from the satellite group that did that, and they have to point the telescope that's tracking the satellite. Their pointing accuracy is they have to be on the satellite to within 1 micro arc second. Yes. It's like, holy cow, right? That's really just beyond extraordinary. It's a really extraordinary
It's
experiment.
amazing, yeah.
Let's see. All right, so just some stuff, some good repeater references. You've already seen, we've already talked about some of these. There's the list for what you want. If you want to learn more about the basics of quantum computing, I have an online course. I have a MOOC called Understanding Quantum Computers, and the next run of that actually starts April 1st, next Monday. The course is free unless you want the certificate, and you probably don't want the certificate. We have subtitles. All of it's in originally English, but we have subtitles in Japanese and in Thai. And if anybody wants to translate it in other languages, we would be happy to have that done as well. And Stephanie Vayner's group from TU Delft has a MOOC on quantum internet stuff, which I have not gone through. Have you?
No.
So I can't tell you anything at all about the quality of it because I haven't looked at it. Axel, have you used the course? Any comments on it? What? He's thumbs up, right? Of course, she's his PhD advisor, so right, it's got to be thumbs up, right? I'm certain it's excellent. I just haven't had a chance to look at it. And if you want more on quantum computing, so our MOOC is doesn't have a lot of math in it. It's intended to take you about 20 hours. Excuse me. Ike Chuang and Peter Shore, who are two of the founders of this field, have an edX course on this, and theirs is about 60 hours, and it has more math in it. I've taken a look at some of that. So a good sequence would be to go through mine and then to go through theirs. Would be a reasonable way to do things. Everybody who's here in the room already knows about the existence of this research group. If you are not on the mailing list, we encourage you to get on the mailing list. It's not very high traffic level, it's just in small bursts. As of last week, there were 236 people on the list, which is not bad. And Tracy and I are both on the steering committee for the workshop for quantum repeaters and networks, and the current plan is for the next one of those to be September 5 and 6 on the inland sea in Japan, in a really beautiful location, starting with dinner on the 4th and ending with breakfast on the 7th. We have the website's up and running. We haven't opened registration. We haven't started doing a lot of advertising yet because we've still got some contractual stuff to work out with the hotel. But we're on track to have this happen, and we would love to have you there for the workshop. Done. Any questions you haven't asked yet? We still have 2 minutes and 56 seconds for questions. Does that mean no final questions? Have you all asked all of your questions? Thank you all for being here.
Thank you.
The group meeting is tomorrow, 12:20, I think. Maybe it's 11:20. I'll have to double check. It's on the schedule. That will be downstairs in Congress. See you there. Thank you all for sitting through 2 hours of this.